These are the frequently asked questions for pre-calculus for section 3-4, day 2, with just a few of the word problems here, 51, 63, and 65. So 51 said compute the sound intensity level in decibels for each sound listed in table 3.21. You had to go back and get the formula for decibels from previous material here. So we have beta equals, and then we had 10 logarithm of intensity over initial intensity. So beta here is the sound in decibels. And we were supposed to use an initial intensity of 10 times 10 to the negative 12th. And that was in watts per square meter. Because what we were doing was comparing this, and that's what that proportion is about. We're comparing that with the quietest whisper that most people can hear. So for A, that means we're going to put our 10 to the negative 12th into that formula. That'll be beta equals 10 logarithm of 10 to the negative 12th over 10 to the negative 12th, which is of course 1. So beta equals 10 times the logarithm of 1. Well, this is the logarithm base 10. And you need to think about snail shelling this and saying 10 to the something is 1. Well, that something is 0. So beta equals 10 times 0, which will give us 0. So again, that's the threshold. You know, we won't be able to hear it. We won't hear a sound because that is the threshold. So that has 0 decibels. And then for B, we have 10 to the negative 11. So 10 times the logarithm of 10 to the negative 11 over 10 to the negative 12. And now we know that when we have powers that have the same base here, what we're going to do is we're going to subtract the exponents for division. So negative 11 minus a negative 12 will actually be plus 12. So we have 10 logarithm of 10 to the first. And if you snail shell this, or just think for a second, wait a minute, that's an inverse, then that's going to be 10 times 1, which is 10. So for B, the rustling leaves, we would have 10. For C, 10 times the logarithm of conversation, 10 to the negative 6 over 10 to the negative 12th. So again, we have division, which means subtraction. 10 times the logarithm of negative 6 minus a negative 12 will be 10 to the 6. We have inverses. This will be 10 times 6, which is 60. And all the labels on these will, of course, be decibels for everything that we have here. Then, we'll find some space over here. For D, the school cafeteria, beta is going to equal 10 times the logarithm of 10 to the negative 4th over 10 to the negative 12th. So again, we're going to do some subtraction. So 10 times the logarithm of negative 4 minus a negative 12 will be 10 to the 8th power. And then, of course, we have logarithm base 10 and 10 to the 8th. Those are inverses of each other. So we have 10 times 8, which is 80. E, a jackhammer. We would have 10 logarithm, and we have 10 to the negative 2 over 10 to the negative 12. And again, we're going to be doing some subtraction because we have bases with division. So 10 logarithm of negative 2 minus a negative 12 will be negative 2 plus 12, which would be 10 to the 10th. So these 10s, common logarithm base of 10 and base of 10 are going to cancel out, and we will get 10 times, boy, that is just about unreadable, 10 to the 10th. And because this is bases that match, there's our inverses, and we get 10 times 10, which will be 100 decibels. Again, all of these, the labels will be decibels on, but I don't think you asked for these questions because of the labels. So just make sure you're labeling everything decibels. Last one is the pain threshold for F of 1. So let me go ahead and pain threshold of 1, 10, logarithm 1 over 10 to the negative 12. Well, you can think of that 1 as really being 10 to the 0. So 0 minus a negative 12 will be plus, so that would be 10 logarithm of 10 to the 12th. Again, here's our inverses with that common logarithm, and we see that we will have 10 times 12, which is going to be 120, and we have that there. That was number 51. Number 63 says we are to compute the power regression model for the following data. So pay attention to the fact that they're asking you to do power regression here. So I already have this data in the calculator. Stats, edit, already in there. So stats, calculate, and then we just need to go down and find power regression. And it's going to give us a model and everything that we need. So there's our power regression at A, enter. And since they might be asking me some follow-up questions later, I didn't read the rest of the question in advance here, I'm going to go ahead and store that under variables, y variables, number one, just in case I need that for a follow-up. So it gives me the model. It says when it's y equals a times x to the b, we should be using y equals 2.750 times x to the 5.000 with rounding to 3 decimal places. So kind of a little basic thing there. You look and say, well, I wouldn't put in the 0.000 if I'm punching it in, and no, I wouldn't either. You know, there's our model. So then B says what we want to do is predict the y value associated with x equals 7.1 using that model. So what I'm going to do, since I stored it, is I'm going to hit second table set, and I'm going to have it start up with 7.1, going by point ones, and hit second graph. And in the table, it'll tell me that 7.1 is 49,616. Now, we definitely could have done that by hand. We could put the 7.1 in here and 7.1 and see what we get in that. And we'll just compare it real quick. So if we put that in, we would have 2.750 times 7.1 to the 5th power. And let's see what we get. And there it is, but we do get the 3 decimal places that way. So 307 at the end. So there's B. And we don't know what this data is. It looks like they did some rounding to whole numbers here, but since we don't know, we'll just leave that as is. And then C says re-express that data in terms of the natural logarithms, natural log of x and natural log of y. There isn't going to be anything for us to write down for this, but obviously this is leading to something. So edit and up to the title, and we want to tell it natural log of list 1 and have it calculate that, and it did. So now we go to list 2 all the way up to the name, natural log, second, list 2, recalculate those as natural logs. Now let's see what the follow-up is. The follow-up is we're going to confirm that y equals e to the b times x to the a. Oh, and I see I skipped D. I better go back. So C, we really didn't have anything to write down. D says compute the linear regression model, natural log of y equals a times natural log of x plus b for natural log of x and natural log of y. So with that data that we have in there, stats, calculate, linear regression number 4, and I'm not going to store it this time. You can always just punch it in. And there's our linear regression model with our natural logs in there. So like it says, we should really like write this with that natural log in there. So natural log of y equals, and then our a value is the 5.000, and then we were looking at the natural log of x. Remember, we went ahead and re-expressed that data so that it's not just x anymore, and then plus our b value of 1.012. Looks like so. So now we have that regression model, and the next piece is confirm that e to the b times x to the a is the power regression model that we found in A. All right, so let's see. Why is this working is what they're asking us. So what we want to do is think, okay, well, what numbers did we get for everything here? Because we really want our f of x to equal e to the something times x to the something else. Well, we just found b and a. This is b. And this is a. Right there. So the natural log we just saw is supposed to work this way. Well, let's see if this actually comes out to be 2.750 x to the fifth. Well, we know we've got the x to the fifth part, so let's just check out that e. Second e to the x, and we want it to be 1.012. It didn't grab the 0. There we go. It didn't take the 1. 1.012. And look at that. That would round to 2.751. And if we go back to our initial power regression model, we'll see we're off by 1,000th. So if you're talking about mathematical significance again, a 0 versus 1 in that 1,000th position, no, it's perfectly fine. This is a good model. That is a confirmation that that's taking place when we see that our math leads us to that exact same model that we had. Now 65 says, recall from exercise 55 of section 2.2 that scientists have found the pulse rate of mammals to be a power function of their body weight. Re-express the data in table 3.22 in terms of their common logs and make a scatter plot. I'm going to go ahead and enter this in. I'm going to pause it for a second while I do that. And ready to go. So we're going to re-express this by using the common logarithm, and we're going to see what happens. So now instead of ln, we're going to go back up and put log. So log of list 2, and over to list 1, and log of list 1. So now we have the common logarithms in there. That's our re-expression of the data. And it just said re-express the data and then make a scatter plot of the data of those logarithms that we have. And I just want to see a quick little sketch of what you see in your scatter plots. So second stat plots. Number 1 is already turned on, which is good news. So let's go to the window and take a look at our values. We had a negative 0.7, so maybe I will try negative 2. And then we had a 1.845, so maybe a 3. And then our y values, 1.8573 was the smallest one, so maybe I'll start at 0 for that. 2.6 blah 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 was the highest one, so we'll go to 4. And we will graph. And I have that equation from the previous problem. stored in here. I'm going to clear that out. And there we are. So you would make a little sketch for me. Something along those lines to show me that you were able to get that scatter plot in there. Then it says compute that linear regression model. All right, so stats, calculate, linear regression, keeping in mind that we used common logarithms this time. And there it is. So with that logarithm information, we know that the logarithm of r, whatever that is going to equal a, which is negative 0.297, and that is times the logarithm of w. And then we have plus b, and our b value 2.364. So we have all of that ready to go, and then we see that there's more follow-up. This problem has a lot of follow-up here. So we computed it, and it says superimpose the regression curve on the scatter plot. So this time I probably should have gone ahead and stored it, but I wanted to make sure everybody caught the part there where we could just use the model. So linear regression, going to go down to store regression equation variables, and whoops, one back. Variables, y variables, 1 and 1. Oh, something went wrong again. It's really touchy about me hitting the keys and holding it down for a second, and I usually punch things way too fast here. So number 4, variables, y variables, number 1, enter, enter. There we go. So now it's stored it in there, and when I hit graph, I'm going to see that line of best fit. And it said to superimpose it, so let's go back to our sketch and say, okay, superimposing looks something like that. I've got it all superimposed on there for part C. D says use the regression equation to predict the pulse for a 450 kilogram horse. Well, I look at the chart and I see, yeah, this was all in kilograms. So if I put this information in, log of r equals negative 0.297, log of 450 kilograms for the horse plus 2.364, I should be able to figure out what r is. So I go ahead and do that. Well, if we find, and this you could punch into your calculator because this is common logarithm, when we go ahead and punch all of that in, we get the logarithm of r equals 1.576323674, and yes, I have way more decimals than I need, because now to get my answer, I would need to snail shell. And that would mean I'm going to take 10 to that answer. And when I do that, I get 37.698 beats per minute. And the question was, is that close to the 38 beats per minute reported by A.J. Clark in 1927? And yes, I would answer that as very close. That is very close. And that would be for D still. All of that math was for D. And then E says, why can we use either common logarithm or natural logarithms to re-express data that fit a power regression model? So let me try to get through this so that you'll see why this works. We had y equals a times x to the b. And we know if we take logarithms, and it doesn't matter what logarithm we use, logarithm base 10 or not, the steps would be the same. Logarithm of y equals, we would pull this apart by addition. And then we would bring that power up front of that term. And what we see is this. If I reverse these two, this says we're going to take b times the logarithm of x plus the logarithm of a. And I realize this is just going to be a number. Kind of looks like a 9, so hang on. Once we put a into that, that's just a number. This is x. We're taking the logarithm of it, but it's still x. B is going to be a numerical value that's in front of that. So when I look at this, I'm really thinking this is still y equals mx, but I don't want to use b because we're already using that as part of this process. This is y equals mx plus c, which is really y equals mx plus b, which is linear. So this is clearly linear. It's still an x to the first that we're putting in there. We're still just putting two numbers in front so that we can get a linear model, where in this case m is going to be b. That's what's in the slot for the slope. C is going to equal the log of a because that's what's in this last position. Y is now equal to the logarithm of y, and x is equal to the logarithm of x. But this is clearly linear. We did not suddenly come up with an x squared or some kind of power for our model. It's still just y equals mx plus b. We can see that when we tear it apart. That's the end of that one.